All right, we're gonna pick up with review for the final with chapter 7. So we have chapters 7, 8, and 9 left, and we'll just try to break this down chapter by chapter. Chapter 7 was a really big chapter. There were like 6 major topics within this one chapter, and the whole chapter was on energy, reaction rates, and understanding equilibrium. Le Chatelier's principle falls under that. But we basically started by saying, okay, just because you can write and balance a chemical equation, that doesn't mean it's going to happen, okay? I could write an equation, for example, of gold, Au, which is a solid, plus H2O. And I could write a balanced equation for this, but just because I can write an equation for this doesn't mean if I drop a gold ring into water, you're going to get a reaction, okay? That was actually the example I used from lecture. So we said there must be something else that plays a factor in determining whether a reaction will occur or not, and that is energy. From an energy standpoint, we can determine if a reaction will occur, if it's going to be favorable or spontaneous. So if you remember the law of conservation of energy, energy cannot be created or destroyed, so the amount of energy that is present within your reactants has to equal the same amount of energy, or the amount of energy within the bonds of your reactants, okay? And the amount of energy released upon forming the bonds of your products. No energy is created or destroyed. Energy can change forms. It can be released as heat. It can be stored as potential energy in chemical bonds. But the law of conservation energy applies, okay? So I have this statement right beneath the law of conservation of energy. Blank, doing what to bonds requires energy, and doing what to bonds releases energy, okay? So it's either breaking or forming. And I'll tell you here, breaking bonds requires energy. To break the bonds of our reactants, we have to invest energy. And forming bonds releases energy, okay? Whenever we form a bond, we give off energy. So remember that. The next big thing we got into was understanding. If we're going to understand energy within chemical reactions, there's 3 terms: enthalpy, entropy, and Gibbs free energy, that were all built together to give us the full big picture of how reactions happen from an energy standpoint. So the first term was enthalpy. All right, enthalpy is H. And our change in enthalpy as a reaction happens is what we call delta H, okay? So the big thing from chapter 7 here is you need to know how to calculate delta H. Delta H is the sum of the enthalpy of the reactants. Okay, you add up all the bond dissociation energy for every kind of bond and the number of bonds you have on the reactant side, and you add all of that up, and then you subtract off the sum of the enthalpy of the products. Okay, these little Greek symbols here just indicate that we're taking a sum. All right, so enthalpy of the reactants minus enthalpy of the products gives you delta H. Remember that if delta H overall is positive, it must mean that enthalpy of the reactants was a larger number, and therefore this is what we call an endothermic reaction. Here delta H is positive. If delta H is negative, that means that the enthalpy of the products was larger, and that means you have an exothermic reaction. It means we're giving off energy overall. Okay, endothermic, you're absorbing energy overall. Exothermic, you're giving off energy overall. We always view things from the viewpoint or the standpoint of the system, which is our chemical reaction. In this case, we are the surroundings, but we're viewing things from the viewpoint of our chemical reaction. All right, so know how to calculate delta H. We had a whole dry lab on calculating enthalpy. So I notice I don't have any practice problems listed. directly on these slides. The textbook problems that I sent out in an email on a document, I believe yesterday or the day before, contain some chapter 7 problems that might include calculating delta H, but I know we had a whole dry lab on enthalpy that would be good practice. If you want to practice, you can just re-download that or print that off, or just look at it and work them on your own paper. Okay, next, delta S, okay, or S we know is entropy, and entropy is a measure of disorder, all right? I'm actually going to write that over here. Entropy is S, and this is a measure of disorder. Okay, so we had enthalpy, now we have entropy, and delta S is change in entropy for a chemical reaction as you go from reactants to products. Now remember, when determining the sign of delta S for a reaction, you must consider two things. One, the number of moles on both sides of the equation, on each side of the equation or the reaction. And then you also must consider the state of matter for your reactants and products. Okay, so remember this, that entropy increases as you go from solid to liquid to gas. Okay, gases are most disordered, so entropy increases as you go that way. Entropy decreases as we go the opposite way. As you go from a gas back to a liquid, back to a solid, entropy is decreasing, you're becoming more ordered. Or as you go from fewer moles of stuff to more moles of stuff, entropy increases. But if you have more moles of stuff, reactants, on your reactant side, and on the product side you have fewer moles, entropy is decreasing. So this is a figure from your textbook. Make sure you know these things when you consider how do you determine the sign on delta S. Make sure you review those things, and you can confidently look at any chemical reaction and determine, is delta S positive or negative. Okay, lastly, we had to learn how to calculate delta G, Gibbs free energy, from delta H and delta S. So remember, the equation is this: delta G equals delta H minus the temperature in Kelvin delta S. Okay, so this is Kelvin. Alright, so two things to check for before you calculate delta G. Is your temperature in Kelvin? Or is it in Celsius or Fahrenheit? Okay, so if it's not in Kelvin, you've got to convert it to Kelvin. And then number two, do you have the same units on delta H and delta S? Whoops, I wrote a D for delta. Okay, so they both need to be in kcal or kilojoules or calories or joules, all right? So you're gonna you usually always have to convert one to match the other. A lot of the times I'll pick delta S and I'll convert it to match delta H. Delta H is normally given in kcal or kilojoules, and delta S is usually given in calories or joules, all right? So keep that in mind. And then these vocabulary terms, endergonic, exergonic. Endergonic is a positive delta G. Exergonic is a negative delta G. Remember, this one is always spontaneous. And a positive delta G is never spontaneous. Okay. Here's another practice problem for Chapter 7 stuff. It says the following reaction is used in the industrial synthesis of polyvinyl chloride, PVC polymer. First question is delta S positive or negative for this process? So let's look at our reaction. We have all of our reactants are gases, and I think it should be balanced. Yeah, everything is balanced. So all of our reactants are gas. So we have 2 moles of gas on the reactant side, and we have 1 mole of liquid on the product side. So remember, as you go from gas to liquid, entropy decreases. So delta S here is negative. Okay. Also, delta H is negative. Part B says, is this process spontaneous at all temperatures? Explain. Well, we don't have a value for delta S. We do have a value for delta H, but that won't help us if we don't know the temperature. It says at all temperatures. But I can tell you this. Let's look at our equation. If we just plug these signs into our equation, so we know that delta G is going to equal, here it's a negative delta H minus, and then we have temperature, which is always going to be positive, times a negative delta S. So let's look at what's going on with the signs here. Delta H will be negative, but because temperature is positive, delta S is negative. That gives us a negative number in the brackets. But we also have a minus sign out front, and a minus negative makes a positive. All right, so we have a negative delta H term. Whoops. And we have a positive T delta S term. Now, so this plus this overall, when we factor in all the signs. Now, delta H and delta S are not going to change. But the one thing we can manipulate is temperature. So if temperature, if temperature is really small, then that might mean that the T delta S unit or term is smaller than the delta H. Okay, so at low temperatures we would get, let's just say at low temperatures, delta G may be negative. But at higher temperatures, at some point, if we crank the temperature up high enough, then the T delta S term will be larger than delta H. And that would mean at high temperatures, we would get a positive delta G. So the question, is this process spontaneous at all temperatures? No. Okay, it will only be spontaneous it'll only be spontaneous at low temperatures. All right, where your delta H, your negative delta H,